All right. Did you get it? Okay, that's all that matters. Okay, so let's talk about the lab from yesterday. So hopefully, your position time graph looks something like this-ish. And probably your velocity time graph looks something like this. Okay? Position time velocity. Now, here's the big idea, okay? Is that both graphs have to show the same thing happening at the same time, okay? That's the most vital thing that you have to understand. You can't have one graph showing constant velocity and the other graph showing accelerated motion at the same time. Okay? It won't work, right? They have to show the same thing happening at the same time. So, start with this idea. So, here was the constant velocity cart, okay, right? Here we go. We had the tape timer, all this good stuff. So, what was the initial velocity vector of the cart? Do not make this difficult.
0.
There wasn't one, right? There was no initial velocity vector. Now, you turn on the switch, immediately what happens?
Starts moving.
Okay. Now, so let's say it's going to move in this direction. So what I can do, and I'm going to do this a lot, I'm going to draw V1, okay? All this says is that, hey, this thing starts to move, and it's going to have some initial velocity. That's all. Now, you don't have to do this, but eventually we will. And then, as it goes faster, what do you think happens to the magnitude of that vector?
It's bigger.
It gets bigger. Oh, right? Now we're out here at V2. Eventually, we're going to be out here at V3. Now, eventually, if it's a true constant velocity machine, what's going to happen to the magnitude of those vectors? They'll stay the same, right? Now, every type of motion that you are going to study in this class is only one of two things. And literally, there are only two tricks. You're either at a you're either at a hairball, okay. You're either at constant velocity, meaning that it's moving in a straight line and the velocity vectors aren't changing, or you have accelerated motion. That's it. Those are every motion that you are going to study in this class between now and December are only one of two things. That's it. There is nothing in between. Okay? Now, we're not going to worry about changing the direction of this stuff until like after the end of the second 9 weeks. So every time that we're going to talk about acceleration, we're going to be talking about changing the magnitude of that vector. Okay. So you're starting here, you have no velocity vector, and then you get velocity vectors and they get bigger. Now, the other thing that we're going to worry about is our acceleration vectors. Acceleration vectors are also vector quantities because they have magnitude and they have direction. Now, even though we haven't talked about this, let's just kind of do a gut feeling. This thing is getting faster going in this direction. And if you define that direction as being positive, cool, make it positive, we're good. So here's the first big question. The acceleration vectors are going to point in one of two directions. They're either going to point in the same direction that the velocity vectors are going, or your your acceleration vectors point in the opposite direction of the velocity vectors. Okay, that's it. Those are the only two games in town. Your acceleration vector points in the same direction, or they point in opposite direction. That's it. Nothing else. Okay, it's a binary function. You got a 50-50 shot. Okay, that's it. So, Mary, do you think your acceleration vectors are going to point to the right or to the left?
To the right.
Beautiful answer. Why?
Because it's speeding up.
Okay, so what?
So your velocity's changing and getting bigger.
So why do you think the acceleration vector points in that same direction?
Because that's the same sign.
Oh, beautiful. Nice. Right? Okay? Because remember, when something speeds up, what do you know about the sign of velocity and acceleration? They're the same, right? So if this thing is speeding up in this direction, that means my acceleration vectors are also going to point in that direction, because that's what's making them bigger. So here's the gig. If your acceleration vectors point in the same direction as your velocity vectors, you speed up. If your acceleration vectors point in the opposite direction, you're going to Slow down. That's it. That's it. So ask yourself, how is this thing speeding up? Oh yeah. Okay, great. Acceleration and velocity pointing in the same direction. Oh, it slows down. Guess what? Velocity and acceleration point in the opposite direction. That's it. There's no other variation on the theme. Okay? I'll never say, oh, acceleration and velocity point in the same direction. Oh, but we're making it slow down. No. Okay? It won't work. So if you watch that cart speed up, oh, acceleration and velocity, all right, they're going in the same direction. Not. It's going in opposite directions. Okay. So this is one way that we're going to represent motion, okay, with these series of velocity vectors. So here's what's critical. So if you look on the bottom of that page, and I say on question number 5, write an explanation to describe what can be deduced by the shape of the position time graph, any changes in slope, what can be concluded, explaining regions where the slope is constant. Go back to the basic definition of slope. What units is the slope of this graph going to be measured in?
Velocity.
Velocity, centimeters per interval, which is going to represent
Velocity.
velocity. So here's the deal, and we'll talk about this today. If you look at this in terms of like tangent lines, okay, so imagine like this is a circle. So if I take this ruler and I move that where I'm continuously drawing like tangent lines to a circle, what do you notice about the steepness of those tangent lines? Are they getting steeper, less steep, or are they just staying the same?
Steeper.
Steeper. So my tangent lines are becoming steeper. So what do you think is happening?
Acceleration.
It's going faster, right? It's speeding up. So this graph shows that it's speeding up by becoming a steeper line. Now, so if this shows you speeding up, I've got to have the same thing happening on my velocity time graph. Now, what does the slope of a velocity time graph give you?
Acceleration.
Ah, so in this case, I have positive acceleration, but what else do I have? Positive velocity. So that means I am
Speeding up.
speeding up. So in this region where I'm speeding up, that corresponds to this graph becoming a steeper line. Okay? Now, once this line kind of levels off, what does that indicate?
Constant.
Constant velocity, which is going to show up how on a position time graph?
Constant slope.
Constant slope. Okay? So constant velocity here is horizontal. Constant velocity here is a sloping line. Okay? Now, so this is one of the things I want to look for on question number 5. You should address the fact that at the beginning, my line curved up to indicate that it's going faster, right? Because the line is becoming more steep. Eventually, what happens to the slope of the line?
Constant.
It becomes constant, which means at that point you have constant velocity. Okay? Now, you need to do the same thing over here with your velocity time graph. Okay? There's this big elephant in the room right here at the beginning. What does that mean? Okay? I don't know. It's a nice graph. No. Okay? So what does this big sloping line here mean? Then what happens when it kind of levels off? So those are the two things that I want addressed. What happens here and what happens up there when it kind of levels off? Okay? Everybody cool with that? Any other questions on the lab? Anything at all you want clarified? Great?
Never mind. Bad.
Probably ask. Ask anyway.
Okay. Number 8. So I
Yeah?
kind of like bounce between no and yes, no and yes. But
Those are your two options. Maybe,
Yeah.
probably not going to work.
right, and so like I was just I guess I understand now, but like
No. Let's talk about number 8.
Yeah.
Okay? I want to make sure everybody is cool with number 8. All right? So on number 8, I say, okay, if the slope of, now this is the slope of a velocity time graph changes sign, does that mean that the cart has changed directions? And then explain, okay? So let's say this is, let me kind of draw that again. Let's say here's your velocity time graph, and let's say it does something like this, okay? So up to this point, what's the sign of my acceleration? Positive. Okay? Once it starts to go down here, I'm going to have negative acceleration. Okay? Now, at this point, listen to me very carefully. Listen to me very carefully. At this point, does the sign of my acceleration change sign? Yes, because I'm going from positive to
Negative.
Here's the question. Just because my acceleration changes sign, does that mean my velocity changes sign?
No.
But Griddle, you shake your head no, and you have this very kind of profound, Socratic look on your face.
I had a good guess. I was impressed with myself.
Okay. So why doesn't it change direction then? It looks like it should.
It's still going like the same
How
direction
do you know it's still going like in the same direction? I like the little hand motion, that's nice.
because it doesn't cross 0 again.
Okay, so what's the very first golden rule? If an object changes direction, the velocity changes sign. Okay, not the sign of acceleration. Okay, not the sign of acceleration, but the sign on velocity. So, even though this starts back down, did the velocity change sign?
No.
No.
No. So did it change direction?
No.
No. But what did change at that point?
Acceleration.
Yeah, I went from speeding up to, but I'm still going in the
Same direction.
same direction. So this is like you driving your car and you hit the brakes. Okay? All you're doing is slowing down. But then you hit the gas pedal again and then you speed back up. But you didn't change direction. Okay? You did not change direction. Cool with that? We're groovy. Okay. Grape, are you good?
Yep.
Anything else? Talk to me, Nick.
Can you explain number 2 again about like the area between the x-axis and like the line?
Yeah, no worries. So here's the velocity time graph, right? So let's say that you've got a horizontal line here at, I don't know, 8 meters per second, and this is 10 seconds, okay? So this is a rectangle that's 8 meters per second high and 10 seconds across. And you're going, whoa, those can't be dimensions. Sure they are. I just did it. They're dimensions. So, Nick, how would you find that area? What would you multiply together?
The 8 and 10
Yeah, but what units is this in?
meters per second.
And this is in,
Seconds.
so what units do you end up in?
Meters.
So
So
therefore,
it's just distance, okay.
no, it's not distance. And here's the reason why. Because if that had been negative 8 meters times 10 seconds, I'd get negative 8 meters. So it's similar to distance, but it's not distance. Let me give you a hint. It rhymes with displacement.
It's just okay, it's placement.
There you go. Yeah, displacement. Comments?
Hi.
Aye.
So on number 10, the one where it's talking about suppose that the batteries run out of energy,
Yeah.
are you wanting it so like, because in a normal case scenario, the car would continue rolling, right? Even after it ran out of batteries.
Yeah,
But we're not worrying about that.
No.
So like it's just a constant drop from velocity from whatever it is, let's just say 2.5 to
yeah,
0.
I'm just worried that you have the correct, that you understand that it's going to go to 0.
Cool.
That's, because you don't know what the scale is or anything else.
All right, thank you.
Okay? Anything else? Go once, go twice, sold. Okay, so, I don't have time for it. So, I hate Wednesday. So, staple the graph to the back and get that into the
All right.
I didn't know.
Hey Matt, stop that.
Dad's going to let us borrow the corporate jet, okay? So, we're going to fly from Wichita to Kansas City. We're going to be in Kansas City for an hour, and then we're going to return back, okay? An hour up, in Kansas City for an hour, and an hour back. So I want to draw the position time graph for this situation. So it's the first thing that we need to establish,
Our reference point,
reference point. What do you want the reference point to be?
Wichita.
Okay? We'll make Wichita the reference point. That's cool. We could have chose Kansas City. Doesn't make any difference. You want Kansas City's position to be positive or negative?
Let's try negative. Let's try negative. Let's make it fun.
Okay?
Let's keep it.
Negative.
Let's keep it positive. Okay? All we gotta do is just, mainly because it's gonna get weird later on if we make it negative.
Oh, okay.
With where we're gonna end up, okay? So, let's make Kansas City be positive, 300 kilometers, okay? Here's 0, here's time, okay? Hours. So, what's the graph gonna look like? Tori, what's the graph gonna look like? We kept it positive just for you, girl. So, what's it gonna look like? Here's 1 hour. There's
It's
2
going to
hours, there's
be
3 hours.
a positive.
Yes. Where's it gonna start?
0.
Here. Okay. Then what's it gonna do? Go up. How far? To maybe 300, because that's where Kansas City is?
Yeah.
How long is that gonna take?
3. Nope, 1 hour.
1 hour. This is gonna take us 1 hour to get to Kansas City. Right?
Uh-huh.
Good so far.
Sure.
So, you say that with no confidence whatsoever. Okay? So, at the end of 1 hour, I am 300 kilometers away from where I started.
Yeah.
Right? So, can I draw this line connecting these points? Seem reasonable? Okay? So, Tori, what does the slope of a position time graph give me?
Velocity.
Velocity. So what's the velocity of the plane? There's 300 kilometers, right?
Yes.
There's 1 hour.
300
300 what?
meters.
No,
Nope.
no, no. This is in kilometers, right?
Kilometers.
Per,
Seconds. Square.
this is in hours, okay? So I got 300 kilometers per hour.
Hours.
Ah, there you go. Score. Okay. Okay. Now at this point we're going to land, right? So what's that graph going to do when we land and we're stuck in Kansas City?
Horizontal line.
Horizontal line, right? So we're here. So at the end of that time, we need to get back home, right?
Yeah.
We need to get back home. So what's the graph going to do? Olivia, what's the graph going to do?
It's gonna go down.
Like this?
Yes.
Okay, cool. Looks like a trapezoid. Does it show a change in direction?
No.
Have a good day. Sorry. I didn't mean to.
Are you going away from the reference point? Do you come back to the reference point?
Yes.
Do you think you changed direction?
Yes.
Tough to do without it? Okay?
I should have done it negative.
Not Huh?
Okay, but
You
there's,
go all the way around the world.
but then you're still changing direction because you're turning.
Okay, no, shh, no, no, no.
Maybe we should
It's a circle. You're not.
Okay, that is weird. Okay.
It's facts.
Now, so let's say that Dad says, you know, I can't let you borrow the corporate plane. I got to use it. But you can borrow the Lamborghini. It's not a bad trade-off. Okay. So if you're in the
Shifting.
okay, gosh.
They
Paddle
got flappy
shifter
paddles
or-
now.
It would be a paddle shift, you're right.
Okay. So you're in the Lamborghini, and let's say it takes, because even though you're in the Lamborghini, you're not going to speed. Whatever. It's my story. Go with it. So it's going to take you 3 hours to get to Kansas City, and 3 hours to get back. But you're still going to be in Kansas City for an hour. Okay? So it's 3 hours up. You're in Kansas City for an hour, and you're back for 3 hours. So what's the graph going to look like?
Taller, skinnier.
A taller, skinnier trapezoidal.
Same height, longer.
No, more like a period.
It's gonna be like 3 times longer. Yeah.
Yeah.
Olivia?
It'll be spread out more
Why?
because it'll take you longer to get there.
Okay, so instead of getting there in 1 hour, I'm gonna get there in 3 hours. Okay? Huh. So this is gonna be out here at 3 hours, right? Okay? So we got some action like this. We're still gonna stay in Kansas City for an hour. And then we're going to come back. So is it still gonna be the same general shape?
Yes.
Just more spread out?
Yes.
Is my displacement the same?
Yes.
Yeah, because I still go from 0 to 300 and 300 back to 0. So the only thing that changes is the rate at which my position changes. In the jet, my position changes very rapidly as a function of time. In the Lamborghini, oh, God, oh. Yep. Yep. He already left. All right. Because I answered the phone?
No, because they keep on calling us and interrupting class.
You should flunk him because he wants class to be interrupted.
No, I'm just making fun of the
I got
office.
you guys.
Okay. All right. So, now let's say you go to the airplane and Dad says, no, not going to happen. He says, how about the Lamborghini? Dad says, oh, no, not going to happen either. And Dad goes, here's the story. You know where you want to go? We got old silver out of the corral out back. Okay? Old silver. Not even like young silver. We got old silver. Okay? So you say, hey, I'm desperate to get to Kansas City. Beats walking, right? So you throw a saddle on old silver and away you go. So what's the graph going to look like if you ride the horse to Kansas City?
It's gonna go halfway because the horse is
Right?
gonna
It's
die.
going to go, right? It'll take a long time to get there. Will you get there?
Yeah.
How many days do you think
Well,
it takes?
unless you die.
Unless you do.
Unless the horse
You
dies.
can probably do it in a couple
Horse is old.
Yeah.
pretty easily. Okay. Got this idea. Now, I would argue that the flight to Kansas City, assuming that Dad does let you take the plane, that the flight to Kansas City on your position time graph actually looks like this. And there's like 1 hour, there's 2 hours, there's 3 hours. So how can the graph look like that?
Because you're slowing down the land.
Because what?
You like speed up a lot, and then you go at a constant rate, and then you slow down because you gotta land. You can't.
No, it's a position time graph.
Oh, position.
It's a
I'm dumb.
position time graph.
Oh, are you
Whoa, what about it?
Point is Kansas City.
No.
are you looking at the sky? So like that's your height?
Well, if your
I mean,
position,
like-
if your reference point
Not
is
in
the ground,
Colorado, man.
then
Well, I'm talking about like that's how you're going
a
up because
plane's
you
little on
ascend,
the road.
then you go down. You get my
He scored actually.
you get my thought process though with that?
I understand.
Okay, so let's keep going.
Because wouldn't that be like how you're going up because you ascend up into the sky, and
do.
so yeah,
And then
you're about there, and then you descend to land,
yeah,
and then you're there for another hour, and then you ascend back up into the sky at a high rate. Then you're at a constant height, and you descend.
okay. It's a nice explanation. But what did we do? Yeah, physics class. Yeah, there you go. Okay. Okay. Maybe little 60s, you do a little finger stack. Okay. Little poetry reading. Okay. You get your phones out. You're doing this. Okay. All right. So. What? Yeah, no, that would be bad. Yeah, the superintendent walks in, my physics class is doing this with lighters. That'd be a hard one to explain. Okay. Oh, your watches?
Yeah,
Oh, there you go, that's not bad.
I don't have my phone on me, so.
Okay, all right. All right, so here's the deal. So what we did is that we shifted the perspective on, if you think about what was happening on that first graph, And this is what happened on the lab that you all did yesterday. It's like you were looking down from on high, right? You were looking down at the cart and you were seeing it start here and you were seeing it go away from that reference point, okay? You weren't looking at the side, you were looking down and saying, okay, it's here and it's going to go away from that reference point. Because the graph that you all drew yesterday, your position time graph, looks something like this. But does this mean the cart went up a ramp like this? No, it means that you were talking about a horizontal position as a function of time. Okay? So it's like you were looking down and it's here and it's going to go in one direction. That's what you were looking at. So, and the same thing is true here. You're looking down, you're seeing the plane start at Wichita, you're seeing the plane go to Kansas City, stay there, and come back. So this has nothing whatsoever to do with the fact that the plane is flying. It's the exact same shape. Plane, trains, silver, whatever. Okay? Still the same shape, you just spread that out more. So, but if you're looking at the side perspective and say, okay, so here's airplane Al, right? So he's here, he's going to fly, right? And then he's going to cruise at altitude to Kansas City, and then what's he going to do? He's going to land. Then what? Chill for an hour, so he's going to be on the ground in Kansas City. Then what? He's go back up, cruise at altitude, and land. Okay? So here's what's different about this, because you're keeping track of vertical position as a function of time. So when this graph goes up, the plane is physically going up in the air. When it's horizontal, the plane is still moving, but it's not changing relative to the Earth. When this thing lands, it comes down. So if this is vertical position versus time, let's get into Lamborghini, okay? If you were to draw this same graph in the Lamborghini, driving to Kansas City, keeping in mind that you were in Kansas, what would that line look like?
Flat line.
Yeah, okay? If you were to drive it, it would be like, we're driving, okay, Flint Hills, okay, come back, Flint Hills, and that's about it. Because from the Earth's perspective, you're not changing. They've asked somebody who was really, really bored, and they did a study of like, if you take the state of Kansas and compare it to a pancake, like on the same scale, like the surface of a pancake, we are actually flatter than the surface of a pancake on a relative scale.
Oh,
okay?
Yeah, I read that, but then they did something more, and it turned out every other state, according to that data, was flatter than a pancake.
I can't believe Colorado would be.
Well, they said every other.
Every
state,
other.
like 25 out of 30, 25 out of 50.
He meant every
Every
other
other
state, like
Not-
that is
not like
the
in a
United
list
States.
and you're-
Not like in a list and it's just like every other state.
But isn't like Florida flatter
I like
than
this
us?
fact.
Yeah, Florida's pretty flat, because that's why they're kind of in a world of hurt if you get into like oceans rising.
Yeah.
Because they're so flat. It's like, how'd that work for you guys? Yeah. But there's a reason that the Native American Indians never built along the coast of Florida. You
Yeah.
know why? Bad things happen.
Yeah.
Okay. All right. See, so
Just,
here's the deal.
Talking about getting rid of Florida.
yeah, we don't want it.
About what?
Getting rid of Florida.
It's way overrated, really.
Yeah.
But they
Oh
have
yeah,
Disney
but
World.
just you have Disneyland in California.
And California is a better state anyway.
That's the
Maybe it's better than
state that we need to keep.
Kansas.
too.
Well, I mean, either way, just get rid of Disney. That's a good one.
Okay, well, let's leave Disney out. Okay, all right. So you got this idea. So you get two completely different shapes of graph depending upon if you're talking about vertical versus time or horizontal versus time. Got it? Okay, now shut that down. Let's go back to yonder roller. Okay, so here's the deal. So for those of you that have ridden on roller coasters, hi.
It was crowded.
Okay. Or understand the concept of roller coasters. What provides the thrill of a roller coaster?
Near-death
Excel-
experiences.
Okay. Accelerated motion or constant velocity?
Accelerated motion.
Accelerated motion, right? Constant velocity roller coasters don't sell very well because you go in a straight line at a constant speed. Now, if that's like the speed of light, okay, legitimate, that would be a cool deal. Maybe even if you break the sound barrier. But that's not the point. So roller coasters change your velocity vector. They make it bigger they make it smaller, and they change the direction of that vector. That's what you pay to do. Okay, that's what roller coasters are doing. So we're going to look at this roller coaster from here to here. Okay, just the little segment of it. So I'm going to start it up here. Okay, whoop, and we'll go up to here. So we're going from here to here. And we need to draw a position time graph to describe that motion. So what's the first thing that we need to decide?
Our
Reference
perspective.
point.
Not the reference point, but somebody else say it. Perspective.
Yeah.
Which perspective do you want to talk about? The horizontal or the vertical?
Vertical.
Vertical, okay. We'll talk about the vertical first. So if we're going to talk about the vertical, then what do we have to decide?
Reference point.
Reference point. Do you want the reference point to be the ground or where you start?
Ground.
Okay? All right, so here's what you've got. So think this through. We're talking about the vertical versus time. So we're here, right? We're going through it. So did it change direction vertically?
Yes.
Yes.
How many times?
3 times, I think. Was it?
Twice.
4. Yeah, 4 times.
Okay, that's okay.
Right?
It happens. Now, let's look, okay? So, okay. Right. So, here's my position time graph. And we're going to be talking about vertical, right? Versus time. So, if you're going to make the ground the reference point, where are you going to start?
About, yeah, around the top.
Yayish?
Way up.
Yeah.
Yeah.
Okay.
All the way.
Then what's it going to do?
It's gonna go down.
Down.
Like this?
Yes.
Yeah.
Okay? Then what?
It's gonna go up.
Like halfway up.
Why only halfway up?
Because it
Because
doesn't go
it's
all the
not
way
as
up to the
high.
top. It's only like half.
Okay? So maybe like yay,
Yep.
Yeah.
Then
Coming
back
back
down.
down.
Back down.
and then back down?
Yeah.
Yes.
Okay? I like how you guys are just, okay, I'm about done. Okay? And then what?
It starts
Goes
coming
up
back
just
up
a
a
little
little.
Goes back up just a little bit. Like that?
Yeah.
Yes.
Yeah, okay.
Yeah.
Yeah. All right. So how many direction changes are there?
3, right?
Well, what would you say your initial direction is at the beginning?
I'm just saying you're up here, and then you're just going to go there. This isn't a direction change.
Okay.
So they're going to be 3.
3.
Yeah.
Now, for those of you that are math nerds, if this was a graph, what would you call this point, that point, and that point? Relative mins and relative maxes, right? Now, so one of the things we'll talk about on a position time graph, because the velocity is always changing, and you can draw what we call tangent lines, okay? Tangent lines allow you to calculate like what we call an instantaneous velocity. So anytime you can draw a tangent line, okay? So imagine like this is a circle, and you draw a tangent line like that. Anytime you can draw a tangent line that has a horizontal slope of 0, what do you think is going to happen?
Direction is going to change.
You can change direction. Because what was the slope coming down, what was the sign of the slope coming down to this point? Negative. So I had negative velocity. Negative velocity. After this point I had positive velocity. Then I've got negative velocity. Now, did my velocity change sign?
Yes.
So if your velocity changes sign, what do you have to do? Change direction. Okay, right? So then I'm going to get another direction change here. True?
Yes.
Okay. Now, that's kind of cool. So here's the question. If you just looked at that, would you think that there was a loop? If this is all you saw, could you conclude that there was a loop?
No.
No. What could be happening to generate this? Yeah, there could just be a hill. Okay, it could just be coming down, going into the hill, going up, and coming back down and going up a little bit. So if that's all you saw, you don't necessarily know that there is a loop. You just know this going down and coming back up. Okay, well that's kind of cool. All right, we got that one. We're good. Okay. Now, but there's a loop. How could would it be legal, whatever, to take this line and bring it back like that?
No.
No.
Why not?
Back in
We're not going back to the future, Marty.
Okay, Marty McFly, okay? So, here's the deal. You can't go back in time, right? Now, for those of you that, again, that are math nerds, what do you call when you try and draw a line to see if it crosses a certain number of points? What? You said it.
Vertical line.
Vertical line test, right? If something's a function, how many times will a line cross a vertical? Once. Because here's where this gets weird. If you try and bring this back, right, you draw that line, what are you saying about at this point in time? Where's this thing at?
Two places at once.
Two places at once, which would be cool, okay? Don't get me wrong. But we can't pull that off yet. So even though there's a loop, we can't show it. The only thing we can show is that it's going down, hitting the bottom, going back up, going back down, going back up a little bit. Good with that? Okay. Now, we're going to do the same thing again, but now we're going to look at horizontal motion versus time. So, we're here, right? Okay. Well, that was a good one. So, what's my horizontal position time graph going to look like? So what's the first thing we have to establish? Reference point, right? What do you want the reference point to be? The end, the middle, or where we start?
Where we start.
Okay, cool. So what's that graph going to look like? Like the roller coaster, almost.
Yeah.
Well, it's gonna never go back down. It's always gonna keep on increasing.
No, it's going to go down around the loop because it's going backwards.
Oh, I guess that is true.
And that's how you know there's a loop if you're looking at this graph. Yeah.
Okay, so we're talking horizontal position versus
Got
time.
a loop.
Now, what did you say?
I said if it was going to look like a roller coaster, we'd have to start the reference point at the end.
Okay? But we're starting the reference point here, right? So, if we're going to make this the reference point at time 0, where are we at? 0. Okay? So if that's the case, then when I do a position time graph with horizontal,
Oh, I can do that.
okay,
It totally works.
versus time. So I'm going to be here, right?
Yeah.
So what's the graph going to do?
It's gonna go up.
It's going to go up, okay? Then what?
Then it's
Back
gonna
down.
start. It's gonna be a little bit horizontal, but a little bit back down as well.
Okay, something like this maybe?
Yeah.
Okay? Now, at this point, what's the cart, where is it at on that roller coaster?
It's at the far end.
Top of the loop?
It's at the far
Or the
end.
side of the loop?
The side of the loop.
Why the side?
Because that's the farthest point from this.
Because here's the deal. So, it's going away, right? Going away, going away, going away until it hits this point right here, right? Then what's it going to do?
Change direction.
It's okay. Then it's going to start to go back. Is it going to go all the way back to the reference point?
No.
No. So it's going to hit this point, and then what's it going to do?
Change direction.
Then it's going to go away again. Is it going to come back? No. So this is like a one-way ticket, right? So you're starting here. You go away from the reference point, then you can go back towards it, and then you're going to go away. All right. Now, when you're talking horizontal, here's one way to think about this. Imagine that you're in a hot air balloon up above, and you're looking down on the roller coaster. And you cannot judge what's happening in depth. The only thing that you can judge is what's happening horizontally. So it's like you're up there, you're seeing it going away, you're seeing it going back, and then you're going to see it go forward again. Okay? That's the only thing that you can judge. So, if you look at this, we start, now here's the dichotomy. Even though we're starting up above the ground, this graph starts at 0. Because that's what we're making the horizontal reference point. So then we're going to go away from the reference point, then what? Then we're going to go back, or we're going to go all the way back?
No.
No. We're going to go some ways back, right? And then what's going to happen?
Change
Go
direction.
back.
Go away.
So how many direction changes are there horizontally?
2.
2. Here's one relative max, there's one relative min. Okay? Good with that. Now, if this was all you saw, okay, and here's what you have to be careful of in comparing these two graphs. If it's vertical versus time, when this graph is up in the air, that roller coaster is up in the air. When this thing is falling, it's falling. When it's going up, it's going up. Now, with this graph, since it's horizontal versus time, when this graph goes up, does that mean that the cart is going up in the air? Well, no. What's the only thing that you know?
It's going away from the reference.
It's going away from the reference point. That's the only thing that you can figure out. You don't know height, right? So here's the question. Could I make this curve on a horizontal position versus time without the loop?
If it's spun this
Yeah,
way.
you go.
Spiral.
How? What if I put it into like a horizontal spiral? If I put it into a horizontal spiral, right, it would go away, it would hit the horizontal spiral, and then it would come back, and then it would hit the far end of the horizontal spiral, and then go forward again. So, looking at each individual graph, if that's all you saw, you don't know that there's a loop, okay? But here's what you can do. If you like superimpose the two graphs and go, okay, hey, in some amount of time, okay, here's what's happening. This thing is going down, going up, going down. At the same time, I've got a direction change going horizontally. So if in the same time intervals, you've got a vertical change and you've got a horizontal change, what's the only way that can happen? Is if you've got a vertical loop. Okay? Now, this one starts going up a hill. Does this necessarily mean that you're going into a loop? No, because if you look at this one, at that same time, what's this one doing?
Towards the
Yeah,
reference point.
yeah, you're just going away from the reference point. So this one going into a hill just says you're going in one direction, right? Because I'm not changing it horizontally because this one doesn't change sign. Got it? Good? Okay, shut that down. Back we go.
Bootleg emoji.
Okay. Now, we need to look at two different situations. Are we rolling?
Yeah.
Okay. Accelerated motion and constant velocity. So here's the million-dollar question. This is a position time graph. Is that constant velocity?
I would take a guess. Yes.
Looks
Yes.
like it.
Why, Madeline?
Because the slope represents velocity and the slope is constant.
Yeah. Okay? So if I go from 0, 0 to 6 meters in 2 seconds, okay? Right? What's the slope of the line in a physics classroom? 3 foot? I know the feeling. Okay? So the slope of this line is going to be 3 meters per second. Okay? Now, here's the question. Does it make any difference which point in time I pick to determine the velocity of the cart? In other words, is the velocity the same at 1 second as it is at 2 seconds?
Yes.
Yes. Why?
Because it's constant.
Yeah, the slope isn't changing, right? The slope is not changing. It's not going to change. But what if I take this line and I do this? Okay? What's happening all up here?
Changing velocity.
Changing velocity. Am I going to change direction? Yes. Now, this is going to be a big watershed moment, okay? I'm going to change direction, right? So one of the things we'll talk about is these tangent lines. So remember, if you talk about tangent lines, like here's a circle, and I said, hey, draw a tangent line. And if you're in geometry class, you go, oh, and I'd pick a point on the circle, and you go, oh, here's the radius, and you take your ruler, okay, and you draw the line like this, okay, and you go, oh, cool, there's the tangent line. Then I said, oh, but draw the tangent line down here. Oh, okay, Mr. Brickham, I can do that, okay. I'll draw a tangent line here and here, okay. How many different tangent lines could I draw?
Infinite.
Infinitely number of tangent lines, right? Okay. I'm not going to make you draw infinite numbers of tangent lines, but infinite numbers do. But here's the concept. I can come in here and I can draw tangent lines. So here's what's going to be important. As this approaches the top of this peak, this relative maximum, are you slowing down or are you speeding up?
Slowing down.
How do you know you're slowing down?
Because you're not sitting deep.
The slope is less, right? What are you approaching?
0.
0.
Oh, right. Okay. So once you cross 0, what happens to the sign of the velocity?
Switches.
Changes negative, but then it begins to get bigger. So visualize this, okay? The timing twins are driving home, right? And Magruder was driving, okay? Right? And Shively goes, oh, man, I forgot my physics assignment, right? And Magruder goes, okay, man, I know how important this is to you, right? No, okay? So your steering wheel is broken. The only thing you can do is just go back and forth in one direction, okay? But you're driving, right? And you want to go, and you want to back up to let off Shively so he can get his physics assignment. So you're driving, this is important, you're driving along, right? So you're cruising along, right? And you know you got to go backwards. So what's the first thing you're going to do? Slow down. Oh, you're going to slow down, okay? So if you're going to change direction, there's three things that have to happen. So this is like the last of the golden rules. If you're going to change direction, there are three things that have to happen. So the first one, the riddle is, what did you have to do?
Slow down.
You got to slow down. Okay? You got to slow down. Because if Al is going in this direction, right, and he's going to change the direction, what do you got to do? Slow down. What's the second thing you're going to have to do? You got to stop. Okay? You got to stop. Because if you're going here, right, you got to come back in this direction. Now, it might be instantaneous. Okay? You don't have to go stop. Okay, then I'll come back. Right? So, like, if I throw this Gary the golf ball up in the air, does Gary the golf ball change direction?
Yes.
Does he slow down?
Yes.
When do you think he stops?
Right.
At the top. Then what does he do?
Speeds up.
Speeds up. So the second step is that you stop, and the third step is that you
Speed up.
speed up. Oh, that's kind of catchy. Okay. You can't change this. Okay. Don't even try. Because if you think about it, it's like, oh, I'm going to stop before I slow down. Think that through. Okay? Just think that through. And if you're stopped, what's the only thing that you can do?
Speed up.
Speed up. Okay? That's like, I'm stopped. Okay. I got to speed up. So, this is going to be huge. Okay? So, anytime you see something change direction, these are the steps that have to happen. Now, that's what's happening on this position time graph. At this point, approaching the apex, what are you doing? Oh, you're slowing down. That's cool, right? Then, at the very top, if you drew a tangent line, you would have a slope of
0.
which means you are
Stopped.
And then afterwards, you're going to
Speed up.
Oh, that's kind of cool. Okay. Got this idea. Now, if I said, I want to find the velocity at, let's say, 8 seconds. Okay? I'm just going to pick a point. And let's say that this position over here is at 4 meters. So, if I pick a point here, it doesn't make any difference which point I pick, because the velocity is going to be the same because the slope is the same. Okay? There's no variation on the things. I could pick 3.17521 seconds, and it's going to have the same slope as 1.9 seconds. Not going to change. But when you have a changing velocity, and you want to find what we call an instantaneous velocity, an instantaneous velocity tells you the velocity at a specific point in time. And I promise you, you're going to have to do this on the assignment, on the test, a week from Friday, you're going to have to do this as well. So pay attention. I'm going to say, all right, hey, that's fine. The instantaneous velocity at 8 seconds. Here's the problem. I just can't find the slope of the line because the slope is continuously changing. So what you've got to do is like imagine that you've got a big circle right here. And you're asked to draw the tangent line at that point. So you're going to come in here and you're just going to have to eyeball this. And you're going to draw a tangent. And now, one of these points is 4 meters and 8 seconds. Here's what you cannot do. Listen to me. Do not do what I'm about to do. Don't look at this and go, oh, I'm just going to take 4 meters and divide it by 8 seconds, and my velocity is 0.5 meters per second. Easy peasy, Burkham, what are you ranting and raving about, man? This is cool. Is that right, though? How many points do you have to define a slope?
2.
2. How many points do you have right now?
1.
1. You've got 1 point, okay? Because here's the problem. If you just take the position and divide it by the time, then you're going to say that no matter what line goes through that point, it's always going to have the same slope, which is patently absurd because they don't. But can you use that as 1 point?
Yes.
But then what are you going to have to do? Oh, you pick another point. So you're going to pick another point on that line and say, okay, I'm going to look at this one. I'm going to use this as 1 point. I can use this as the other one, and then I'm going to find the slope of that line. So on your assignment and on the test, I'm going to give you a specific point in time and say, what is the instantaneous velocity at that instant? Hence the term instantaneous. So here's the first thing that you're going to do. Imagine it's a circle. You're going to draw a tangent line. Then what are you going to do?
Find the other point.
Yeah, you're going to pick 2 points on this line and find the slope. Now, if I pick a point, let's say this line comes up like this. Now, if I pick a point over here, let's say that's 12 seconds, and I draw that tangent line, first off, what's the sign of this slope going to be? Positive or negative?
Negative.
Negative. So then when I get over here, I know my velocity has to be a positive number. Okay? Because we went from instantaneous negative velocities to 0 to positive. So did I change direction at that point? Yes. Because I went from negative slope to positive slope. Got it? Okay, so stop that. All right, let me get you through what's going to happen on this assignment. So oddly enough, it's going to deal with roller coasters and tangent lines and all that good stuff. So on the front page, you've got all of your data. What this is giving you is where you are with this roller coaster as a function of time. Okay? So you got horizontal position, vertical position. There you go. So on number 1, first thing we're going to say, we're going to plot a position time graph for movement along the ground. So movement along the ground, do you think I want the horizontal motion or the vertical motion?
Horizontal.
Horizontal. So you're going to go up there and go, oh, right, I got 24 seconds. And you're going to go from 0 out here to 24 seconds. Make this big, especially the first graph, make this big. If you want to take a sheet of paper and just divide it up into thirds and put like graphs on like a third, a third, a third, that's cool. If you want to do like front, back, that's cool. If you want to, if you don't like trees and you want to put one on each one, I don't care. Now, so if you look at your data, so this is a position time graph with horizontal. So if you look at your data, at time 0 horizontally, where are you at?
0.
So you're starting at
0.
the reference point, right?
Yes.
Now, you're going to draw this graph and not to ruin the surprise, but it's going to look something like this initially. Okay? Roughly, this is what it's going to look like. So, and the first thing we're going to say is describe the graph. You don't have to write your doctoral thesis. Okay? What does the graph look like? Okay? Is it a straight line? Is it curved? Does it go up and down? What does it do? Okay? Again, you don't have to, you're not Hemingway writing prose about Africa. You're describing a line. Okay? Got that. Then I'm going to say, is the velocity constant? So right away, is this velocity constant in the horizontal plane?
No.
How do you know?
It's curvy.
It's not linear. The slope is always changing, and then not only are you changing the slope magnitude, but you're also changing the direction. There you go. Now, here's the heart and soul of what you've got to do. So down there on number 3, says at the 8-12 second marks, draw tangent lines to the curve and determine the velocity at those points. Show calculations of slope. So when I type this, here's what I had in mind. Trust me on this one, the 8-second mark is about right here. So, and I've got to tell you a specific point in time. Okay? And this is what's going to happen on the test. I'm going to say, at the 8-second mark, I want to know what the velocity is. Well, I know my velocity is changing at that point, so I just can't find the slope of the line. So what I'm going to do, and this is what you're going to do on this assignment, you're going to go to the 8-second mark, you're going to find this point. You're going to take your ruler, and you're going to kind of eyeball this and go, okay, that tangent line is going to touch that curve at one point, and one point only, at that 8-second mark. Okay? Now, I want you to find the velocity. So after you get that line drawn, what are you going to have to do?
Find 2 points.
You got to find the other point and then find the slope. Now, if you want to, when you go to that 8-second mark, which has a position of 21 meters, you can use that as one of your data points. Because you know at 8 seconds it's at 21 meters. You can use that as one of the data points for your slope, but you got to pick another one somewhere on that graph. Then you're going to do the same thing. What's it? 13? 12. Okay? So the 12-second mark is going to put you somewhere over here. And again, you're going to draw this tangent line, and you're going to find the slope of that line. So right away, what do you notice about the signs of those slopes?
Different.
They're different. The first ones have a
Positive.
second one's going to have a
Negative.
So what did it have to do in between?
Change direction.
Change direction. Right at the apex of that curve. Because that's when you're going to draw a tangent line, which is horizontal. Which leads us to what I want on question number 3. Draw the tangent lines. Okay? Then you're going to take 2 points on there, you're going to find the slope, and you're going to show me, hey, Mr. Burkamp, this is how I found the slope at the 8-second mark, this is how I found the slope at the 12-second mark. Now, on to the back side. Thank you. Bless you. At 9 and 11, you're going to draw tangent lines. If you draw the tangent lines correctly at the 9 and 11 second mark, it's going to be real easy to determine what the velocity is at that point. Notice on number 4, I didn't say, oh, show all calculations. Okay? That's not what I said. Right? I just want to know, hey, what's the velocity going to be at those points? Okay. When you get to number 6, now you're going to draw a different graph. Now you're going to draw vertical position versus time. So if you're going to draw a vertical position versus time, where does that roller coaster start? Vertically.
11 meters.
Yeah, it's going to start way up here. What do you think it's going to do? Yeah, it's going to go down, and what goes down probably ought to come back up. If not, your roller coaster is broken. So, oddly enough, you're going to come in here and you're going to draw the graph. And it's going to ask you, that's all you have to do. You don't have to do anything else with this graph. It's like, is the velocity constant? Yes or no? Yes, it is, because the slope is always the same, or no, it's not, because the slope is continuously changing. I don't care. Pick one. Oh, hopefully based upon logic and not like flip the coin. Now, here's the most important thing. When you get to number 9, okay, this is what gets screwed up the most. On number 9, pay attention to this. Here's your graph paper. Okay? I don't care how you set up the scale on number 9, but it has to be the same. So like if you're going out this way and you're going to let each grid be 2 centimeters, that means when you go up, each one has to be 2 centimeters. You can't have this one being like 2 centimeters and this one being 6 centimeters. Okay? It won't work. Because what you're going to do is that you're going to plot the vertical and the horizontal, but you're not going to include time on number 9. Okay? Time is not a factor on number 9. Basically, you're going to have a series of coordinated pairs, and then you're going to look and go, oh, this is what the roller coaster really looks like. Okay? Now, when you get down to question number 11, okay? Now, listen to me very carefully. In big, bold letters, okay? Number 1, I want you to reference both the position time and the velocity time graph. The other thing that's important is I say, hey, what's happening between 7 and 15 seconds? In other words, I'm giving you a specific point in time, okay? A specific point in time. So, you're going to come to you're going to look at both graphs. You're going to look at what's happening vertically between these times, and you're going to look at what happens horizontally between those times. And then you're going to look at your roller coaster and go, wow, which portion of the roller coaster will allow that to happen? You have to also pay attention that this is going to be in seconds, okay? It's going to be in seconds in terms of these graphs on your x-axis, but on this graph, you're going to have 2 dimensions that are both in meters. So tangent lines here won't do you any good, because you just won't have any units because you'd be taking meters over meters, so it doesn't mean anything. But here's the most important part. You're going to look at this, you're going to have the shape, and then you're going to look at these graphs and go, okay, what's happening in this interval, what's happening here, and then which portion of this graph will allow that to happen. Then you're going to go back to here, and then you're going to look at, I think, what is it, 17 and 24? So you're going to go out here to 17 and 24, and you're going to look at what happens vertically, you're going to look at what happens horizontally, and then you're going to go back to the actual shape of the roller coaster and go, okay, where's it at? Okay? I'm done. You're good? You're on your own.